So it's a big honor for me to be here today. Thank you for inviting me to speak. Before I get started, I wanted to acknowledge my collaborator, Elise Trevette. Elise joined my team about 1.5 years ago as a sterility assurance scientist, and a lot of the content of this presentation is based upon a lot of great work that Elise has done, so thank you, Elise, for that. So I'm going to be talking about sterility assurance considerations for a 3D printed patient-specific bioresorbable implant. So we have a product in the pipeline. It's called a TrueMatch Graft Cage. It's a device intended to treat long bone segmental defects. These defects can result from trauma, cancer, tumor resection, even bad infections that result in resection of bones. So as you can see on the left, there's a model of a bone missing a very large segment, and the graft cage is inserted. This is a patient-specific implant. As I mentioned, it's got osteoconductive properties to help promote bone growth. I'm very proud to say that we have the very first Johnson & Johnson product that's a 3D printed bioresorbable implant that received 510(k) FDA clearance. So that happened earlier this year. So we're really excited about that. The intent of this device is to, if you look in the upper right picture, to hold the bone graft in place, and it helps to make sure that graft stays exactly where it needs to stay during the healing process. And it's intended to be used with rigid fixations such as nails, plates, even external fixation, as you can see in the lower right. So I'm going to steal Wendy's theme here a little bit, called Arts Part to Patient, because I'm going to show you a real-life example of our end-to-end manufacturing process for our 3D printed product. And it starts with the patient's CT scan, which is provided to our company, and we will digitize that image and put it into our software program where the design is created for that implant. At that point, the design goes to the clinician to make sure everything is correct, and the physician will give approval for that. And that's when the clock starts for us with the manufacturing process. So this is our 3D printer. So we print the part. It has a proprietary coating process, after which we have our final implant, which is packaged, put through a sterilization process, out the door to the patient. Piece of cake, right? Maybe not so much. Maybe there's more to it than that. So this is personalized medicine, right? So we need to get it to the patient fast. We have 10 to 14 days from the time we get the clinician-approved design. That's when the clock starts, and we have to get it back to the patient in 10 to 14 days. So we don't have a lot of time to do this. If any of you were here at the Johnson & Johnson Sterility Assurance Conference last year, we had a poster that talked about our choice of sterilization modality, and we went into all of the considerations and the different types of modalities we looked at. We did look at gamma, which not only had property changes to the material, but also takes a little too long, right? We looked at some other possibilities. Some, maybe the material was not compatible due to the heat, or just, the nature of the product was not going to work. So we landed on ethylene oxide as our sterilization choice. So we chose to expedite the process. We put our sterilizer in line with our manufacturing process. We've implemented parametric release. So the biological indicator time frame, just throw that out the window. Don't need that. We have small-scale sterilization because in this case, it's patient-specific. One device pretty much equals one lot. You need to be able to run one device at a time. And we collaborated with the manufacturer 3M and Cosmed Group, and I know Clark's here somewhere. We collaborated with his group back here, so thank you, Clark, for your collaboration on this. And this is actually one of our two sterilizers. They're identical that we have in our inline manufacturing process. It's very cost-effective. I think a small cartridge of EO is somewhere in the neighborhood of $20 or $30. So if we have to run multiple cycles per week, it's very cost-effective. The turnaround is very quick. We also collaborated quite extensively with our Johnson & Johnson sterility assurance partners in Raritan, New Jersey. They helped us develop a cycle which is about 24 hours. So we can get that turned around pretty quickly. It's a very small footprint. It's really not a whole lot larger than the oven that you probably have in your home. Simple operation too. The validated cycle is programmed into the sterilizer, and all the operator needs to do is place the packaged device into the sterilizer, close the door, press the button, and that's pretty much it. And you see, I've got shoebox manufacturing on here. So as we were developing our manufacturing process, the end-to-end process, we were trying to take a strategic approach where if we decided we want to take this particular manufacturing process in its entirety and put it into another Johnson & Johnson facilities anywhere around the world, we would be able to very easily replicate that. For the end-to-end process, we did our typical sterility assurance risk assessment. And for the purpose of this presentation, we chose several different points of interest that either have to do with 3D printing or with the nature of this particular product. And as Wendy had mentioned, with powder bed fusion, which is the type of technology we use more specifically, selective laser sintering, there's a lot of waste at the end of the printing process. So there's a lot of leftover powder. I shouldn't call it waste, because we're not going to let it go to waste. So this is a photograph of what's called our breakout station. So after the part is printed, there's basically a big cube or a cake of powder, and somewhere inside of there is our device. So this is transferred from the printer over to the breakout station. You might want to imagine sort of an archaeological dig, to get into that device. There's a lot of powder that results, as you can see. So that powder is collected. It goes through the sieve into a collection container below. And of course, being microbiologists, we're like, oh, wow, how does that, the potential to use that powder again impact the bioburden or endotoxin level of this product, of the recycled powder? So it reduces cost and minimizes waste, but does it put the patient at risk? We were very concerned about that. Inquiring minds wanted to know. So what we did was we partnered with the Johnson & Johnson 3D Printing Center of Excellence in Jacksonville, Florida. They were running a reuse or recycling study in their pilot lab, which is a completely non-controlled lab. And we said, well, this could be our worst case scenario to test this out. Can we piggyback onto your experiment and do some bioburden and endotoxin testing? And so that's exactly what we did. Had some interesting results. So we tested not only the recycled powder for bioburden and endotoxin, but we also tested parts that were printed using the recycled powder. They did a total of 21 cycles, and we tested at various time points, or cycle points, so cycle 1, 4, 7, 11, 15, and 21. And as you can see, over the course of these 21 cycles, we didn't see any trend that there was an increase in the bioburden. This is strictly for bioburden here. So we were very happy to see bioburden levels did not increase. I didn't even put a slide together for the endotoxin levels because for all of the time points, they were undetectable, or below the limit of detection. So that was very exciting for us. So the bioburden for the powder and the parts remained consistently low for the reuse cycles, and the endotoxin was below the limit of detection for all cycles. The next consideration we're going to talk about is our proprietary coating process. This involves temperature and an aqueous solution that provides conditions that are pretty conducive for microbial growth. So again, we wanted to know, what kind of risk are we looking at here? Our implants can undergo a multi-day coating process. It can be many days. And it's at a nice, warm, toasty 37 degrees Celsius. Of course, we're concerned about the risk for increased bioburden and endotoxin during this process. So the first thing we did was we looked at the process step by step. And what we found is the very first step in the process is a chemical treatment that happens to be antimicrobial in nature. So, hooray, little party with that. That's good news to get us started. And then we said, well, we have to control this water. Let's make sure that we're using high quality water, that we're monitoring. So we're using USP purified water, which is routinely monitored for bioburden, endotoxin, TOC, and conductivity, so that at any point in the process, we would be able to detect a shift and take action immediately. And then the final consideration is there is a coating container that we use, an HDPE container, which we had tried to source pyrogen-free. We were unable to do so in the size that we needed. So we actually worked with the manufacturer of the coating container to ensure they implemented cleaning steps and provide a certificate of this cleaning with every lot that is provided to us. And with every incoming lot of containers, we do an endotoxin test to ensure that it's of appropriate quality. So we did some testing, and we found that the implants that were subjected to our worst case coating process, which is the longest coating process that we could possibly use, and we found that the endotoxin was below the limit of detection, which made us very happy. And the bioburden average was also very low. The coating container was also tested, and a value of 0.66 EU per container is very low. We've actually, since there are no guidelines on what this should be, we have assigned a limit of 20 EU per container, which is equivalent to the limit that is assigned to the device itself. And then the final thing that we looked at, and Jerry and I started talking about this several years ago, actually, so it was exciting to explore this, was, okay, well, this is a bioresorbable implant. So I know we're sterilizing the outside of it. Are we getting to everything that might be inside? Inquiring minds also wanted to know that. So doesn't have to do with 3D printing in particular, but we did find a way to test this, which is really exciting. The exciting part is that we found that the EO absorbs into and through our implant. So we used a proprietary test apparatus that was designed by one of our colleagues at JJSA Raritan. And through this device, we found that EO penetrated through. We had inactivation of the biological indicators that were opposite the graft cage, which acted as a filter, essentially. It was a solid filter. And side by side in this experiment, we used a thin wall metal control. And of course, in the control, all of the BIs were positive. So that was a really exciting finding for us, and that was just like the icing on the cake for us in terms of managing the risk to the manufacturer of this product. So I feel like we have successfully conducted risk management for a successful patient outcome. You know, the recycled raw materials, low risk. We've controlled our bioburden and endotoxin throughout the process. And most excitedly for me, we know that not only is this fast sterilization, but it's also effective all the way through the entire product. And just to show you a little bit about what this product can do, the photographs that you see on the right are from our animal study that we did. And that's an actual defect on the left at the beginning of the experiment. So you can see the graft cage in there and the resulting bone healing on the right. So it's a pretty exciting product. I've been involved with it since the charter of this project, which is 4 years ago this month. I know Wendy was saying, or somebody was saying 2 years. I'm like, I'm sorry, we're not quite that fast yet. But it is exciting to see we're scheduled to launch later this year. So this will be my first ride from the beginning to end of a project. And it's such a cool product too. I'm very excited. So thank you for having me here, and appreciate having the opportunity to share with you.